Welcome everyone to today's Astroparticle seminar. Today we're happy to have Meng-Ru Wu from Academia Sinica in Taiwan. Meng-Ru got his PhD in Minnesota University in the US. Then he was a postdoc at Darmstadt in Germany. Then he was a postdoc here with Irene at the Niels Bohr Institute. And now he's assistant research fellow at Academia Sinica in Taiwan. He's there, the head of the theoretical nuclear particles astrophysics group. And he has worked and continues to work on several aspects of compact object mergers with a focus on neutrinos and nucleosynthesis. Examples include like neutrino flavor evolution, including collective and fast oscillations, nucleosynthesis in supernova, R-process nucleosynthesis in kilonovae and neutron star mergers, and BSM neutrino physics in supernova, including active sterile neutrino mixing, light, beyond static model particles, and dark sector studies. And he's also actually worked on high energy neutrinos, including the GRB contribution to the ice cube flux and boosted light dark matter. And today, we're lucky to have him talk to us about neutron star mergers and the R-process nucleosynthesis. So Meng-Ru, thank you for being here.
Okay, thanks for the invitation and a very complete introduction. And yeah, it's a great pleasure for me to be able to give this talk remotely and to focus a bit more on the aspect of my work on the with collaborators on neutron star mergers and R-process nucleosynthesis. And as we were chatted before the talk, that yeah, I happen to know that look at your seminar website, and then I happen to know that there were already more like 2 R-process talk before, right? So I actually watched a bit of what Amandina talked about, and Jennifer's. I think she did not record a video, so I couldn't see what she was talking about. But anyway, so I tried to try my best to reduce the overlap between this content and what was given in Amandina's talk. Okay, so yeah, so still I would like to give some very short introduction. So we know that the observations of say stellar isotopic and or the elemental abundances from, for example, the solar system. Okay, so solar system on the left, and from say many now more than like many tens or even out of 100 metal poor stars that are having say the iron to hydrogen ratio that is about say 1,000 times smaller than the value of the solar iron to solar metallicity, or from roughly 1,000 to 100 times smaller. They all show the unique feature of the R-process nucleosynthesis element, the presence of R-process nucleosynthesis elements. And for example, in the solar system, you can see that when you decompose the abundance pattern for elements or nuclei heavier than iron, then you see that there are 2 clear different shapes. Okay, so the blue ones where there are like 3 peaks in strontium, barium, and the lead, they are so-called S-process elements that are produced mostly by HB stars, while the red curve shown in this plot has a broader peak, and the peak numbers are located at a bit lower than compared to the S-process elements. And those, like for example, tellurium and the xenon, and the third peak, the gold and the platinum, for example. So those elements are known to produce by the R-process, the rapid neutron capture nucleosynthesis. And then if you look at, if you overplot the solar R-process pattern, on top of the abundance, relative abundance is measured in the surface of several metal poor stars. For example, in the right-hand side, each data point, each data series shows the abundances pattern from one metal poor star, while the solid line is the solar R-process abundances translated from this curve, basically. Then you see that they basically match very well with each other for many of them. So this suggests that yeah, there's a very robust neutron capture, rapid neutron capture nucleosynthesis happening in nature from say many giga years ago up to now. Okay. So we know that why we call it the rapid neutron capture processes is because we know that for this kind of processes to occur, for starting, let's say if we start from a seed nucleus, then it should this kind of nucleosynthesis should happen in very neutron-rich and fast expanding material environment. Okay, so that when the material is expanding, then you have some seed nuclei and a lot of neutrons around. Then the nuclei can capture a number of neutrons before it encounters a beta decay, unless it is in the shell closure number. The neutron number hits the shell closure number, the magic number. Okay, so you can see like in this plot where the x-axis is the neutron number, y-axis is the charge number or atomic number. The R process path was long time ago predicted to be, say, sitting very far away from the from the stable nucleus region. Okay, the stable nucleus region are represented by those dots here. Okay, so the R process paths are very far away from stability. Okay, so one notice that to quantify R process, you are basically comparing the average neutron capture rate versus the average beta decay rate. And for R process to happen, obviously, the average neutron capture rate has to be much bigger than the average beta decay rate. Or conversely, the average R process lifetime is much smaller than the average beta decay lifetime. Okay, so because of this R process happens very far away from the stability, so and it requires a very neutron-rich condition. So the most popular sites for producing those since a long time ago was proposed, including, for example, the neutron star mergers and or supernovae. Both of this type of events include either the production or the death of neutron stars. Okay, so so this was a big question many years ago, but we all know that it was solved. Well, not really solved, but there was finally a first evidence of neutron star mergers. Anyway, so one thing, a note that you probably heard from Almudina's talk was that the outcome of the R process depends pretty much on the astrophysical conditions as well as the nuclear physics inputs. For example, astrophysical conditions, you need to know the neutron richness of the ejecta, expanding material. You need to know the entropy of the expanding material, and you also need to know the expansion time scale of the material. Okay, and then in terms of the nuclear physics, because again, those R process pairs are very far away, basically sitting in the region beyond the current nuclear physics experimental reaches. So the properties of those nuclei are largely unknown, including their masses, their lifetimes, their reaction rates, and or like in the heavy region, the fission property of those nuclei. So all those are still the big uncertainties in terms of robust prediction for the R process outcome from theory. Okay, so we already mentioned that almost like 4 years ago from now, you saw on the news that everywhere in the newspaper people say astronomers, for example, confirms origin of the new universe heaviest element in neutron star mergers, and then you also see probably this cartoon artistic picture long time ago, or many times, that there are like two glowing neutron stars, and then after they collide, then there's a jet in the, say, perpendicular direction to the merging plane, and then there's a expanding material that is glowing in gold, indicating the origin of gold. Okay, so that is like a typical plot that you see from artistic. Okay, so but for us, then when we model the R process or the real observables R process, it is not so easy in the sense that we need to involve many different stages of theoretical calculation in order to compare the theoretical prediction to the observation, right? So for example, there are like 3 plots down here, and illustrating, say, the needed computation at a different, very different physical time scales. Okay, from say roughly time scale of say millisecond to several tenths of millisecond. That is the time scale that the merger simulation need to do, which is basically governed by the dynamical time scale of the compact object. Okay, so those merger simulations, ideally, we would like to include the magnetic fields and the general relativity, as well as the neutrino transports. And another important aspect that is still not yet so clear is the unknown nature of the dense matter. Okay, so all those are big, say, still uncertain aspect in terms of the merger simulation prediction. Okay, so then once people who do those simulations then can predict, for example, the property of the ejecta, of how many materials being ejected during the merger event, and what are the, say, expansion timescale, entropy, and neutron richness, then we can then post-process those data, simulation data, and then use, say, our nuclear reaction network to do the nuclear synthesis computation. Okay, So we already mentioned that the big uncertainties are astrophysical and the nuclear physics. Okay. And then after that, then we can get our, say, our process abundances and the corresponding energy production rate from, say, the decay of the unstable R process nuclei, which is the power, the energy input that actually powers the kilonova, which is the transient associated electromagnetic transient associated with neutron star mergers. Okay, so then those inputs are then further used by the people who do radiative transfer in either simplest way, like a 1D radiative transfer, or the more complete fashion would be doing the multi-D radiative transfer for the kilonova light curve or spectral modeling. Okay, and then once again, there are also many different uncertainties in modeling the kilonova light curve or observables. For example, the atomic opacities, there were already huge effort in the past to try to reduce the uncertainty, but there are still like a factor of a few-ish in terms of the atomic opacity of R process nuclei or elements. And the ejecta mass and velocity and shape are also kind of unknown, so you have to assume something to do the fitting of your theory output to the data. And the predicted energy injection rate can also depend on nuclear physics property, obviously. Okay, so all those different aspects are involved. For example, if you want to use kilonova observation to infer the progenitor property of your two neutron stars, then you have to try your best to include all those different aspects in order to have a good parameter extrapolation. Okay, extraction. Sorry. Yeah. So but then we can still look at broadly what was the evidence of the R process coming out from the GW17 OA17 event. Yeah. So for example, in this plot that was taken from Daniel Kaysen, what it is showing is the spectrum of the observed photons in the optical up to infrared region at the times of roughly 2.5 days after the mergers. Okay, and when Kaysen was fitting his models to the data, he used the so-called two-component models. Okay, so in one of the component, basically two spherically expanding clouds. Okay, and then each of which may have some its own ejecta mass, its own velocity distribution profile, and its own content and lengthened mass fractions. Okay, so why lengthened mass fraction is important? That is because back in 2013, there were two famous work from Jennifer Barnes and Masami Tanaka's et al. They predicted that with the presence of lanthanides and actinides, which are basically those F-shell elements with F-shell valence electrons, then with a tiny presence of those elements, they can largely enhance the thermal photon opacities of the inside the R process inside the merger expanding material, and then this can delay the output of the peak light, and then also shift the spectral peak of the kilonova from, say, optical to infrared. Okay, so as you can see here, like to really fit those data, then in these two component models, you need one component that contains relatively high amount of mass fraction of lanthanides, roughly around 10 to the minus 2. Okay, to produce the to reproduce this infrared part of the spectrum. Well, if you only have like one component that is a mass fraction of lanthanide of, say, 10 to the minus 5, then you will the peak spectrum would be picked around, say, optical-ish. Okay, so there are many works try to do different ways of fittings and the different models, but then roughly speaking, the broad brush conclusion was that the ejecta mass coming from this event being thrown out, baryon number being thrown out, baryon mass being thrown out from this merger event was roughly like 0.05-ish solar mass. And the ejecta roughly expands in the range of, say, 0.1 to 0.3 times speed of light. Okay. So, yeah, so this was basically this lanthanide fraction inferred from this fitting was basically the evidence of the R process. Okay. And so if you look at once again, and then one more thing is that if you look at spectrum, you can see that there's no particular absorption lines or emission lines that can allows you to identify the direct evidence of individual elements like gold, platinum, or anything, right? Okay. And yeah, I already mentioned that uncertainty, there are huge uncertainties in this. Okay, so yeah, that was the status at that time that, well, we say that this is very sort of like featureless spectrum and without a particular trace of individual element. Okay, and then in roughly 2 years ago, in 2019, there was a paper appeared in Nature, where in which they basically, if you compare the spectrum at 2.5 days, yeah, which contains some feature of the bumps and dips here around between say 5,000 angstrom to say 10,000 angstrom. Okay, so they were like peaks and troughs. Okay, and then this group of people then tried to explain the shape of the spectrum by the broad absorption of several different transition lines associated with strengthening. Okay, and then you can see that in their fitting, it actually works quite well. That in the early time where the absorption is stronger than the recombination induced emission, then you have very strong absorption features in the spectrum. While as the time progresses to the later times, then the famous Sipigny features start to appear, where you have the shallower absorption features coupled with stronger emission features coming from the ejecta. So this was interpreted as the by this work as the evidence of the existence of LiDAR process element of strengthening, which is a charge number 30 and the mass number 88. Okay, so because and then this would, if this is true, then this would support that there has to be some weaker interactions that takes effect in the merger ejecta to raise the say electron fraction, which is basically the number of protons relative to the number of total baryons, yeah, to roughly about 0.3. Okay, so this has some implication, potential implication to the roles of neutrinos that we'll discuss a bit more later. Okay, so yeah, so if we believe this phase feature is being associated with strengthening, then that would be, say, the really first evidence of a particular existence of elements of a LiDAR process element inside this kind of kilonova ejecta. Okay, so that's pretty exciting. So yeah, so that was like the introduction part. So try to summarize a bit about the lessons that we learned from the GW17 observation. So yeah, the key point was that this event confirms merger being the source of our process through the lanthanide rich the spectrum at the infrared region, okay, inferring the lanthanides. And then the inferred ejecta mass and velocity are roughly consistent with theory prediction by the general relativistic numerical simulations, okay. And because of the observation of gravitational wave events, the LIGO and Virgos, they can also tell us what are the roughly frequency range of this kind of event to occur, okay. So if you know this, the occurring frequency rate, and if you know how many our process material can be generated in one event, then you can sort of estimate how many our process elements or nuclei are being produced, for example, in the Milky Way galaxy throughout the evolution history of our Milky Way. Then this number are basically roughly consistent with observations. So this also suggests that the neutron star mergers can be the dominant process site, given those inferred frequency and the yields. Okay. However, yeah, that is definitely not the end of the story. Okay, so a few further issues that we would still like to understand better. For example, we have already briefly mentioned a lot of uncertainty sources, right? So we would definitely need improved theory modeling for, say, beta merger parameter extraction if we are going to use the electromagnetic signature to tell us some physics involved in the mergers. Okay, and then we would also like to identify more traces of heavy elements other than, for example, the existence of Strongthian or the European. And the other issues that connect to other astronomical observations, like those in metal poor stars, is that we want to know whether we still need any other process sites other than mergers. Okay. So for the rest of the talk, I will basically try to touch each of those issues a bit based on the work that we did in the past few years. Okay. So, by the way, so if you have any questions, yeah, welcome to just unmute yourself and to ask. Meanwhile, okay. So yeah, the first topic I really want to talk about is the neutrino favor conversions inside merger remnants. Okay. So we know that after two neutron star merges, okay, then there can be a merger remnant that can consist of, say, in the center, a hot hypermassive neutron star like this, or a black hole. Okay. And then because of the angular momentum, initial angular momentum carried initially by the merging system, so the initially being disrupted material and some of them will not be able to fly out right away, and they can fall back into the central remnant. But because of the angular momentum carried away by those, then they will form a thick accretion disk around the central compact object. Okay, so the so-called accretion disks. Okay, and because of during the merging processes, the two neutron stars basically collide with each other with, say, roughly relative velocity of 0.3 c. So there's a very violent collision happening in the collisional interface, and that can heat up the massive neutron star to a central temperature of several tens of MeVs. Okay, and the disk can also undergoing the compression heating, and the central in the mid plane of the disk can also have temperature of, say, 10 MeV-ish. Okay, so then we know that in this kind of highly dense and hot environment, then neutrinos are going to be produced, and because they will be the only standard model particles like escape from this environment, so they will be basically the one that dominates the cooling processes of those merger remnants. Okay. So in fact, there are many, say, numerical simulations that try to model the neutrino emissions or the merger remnant outcome from different simulations. And then they all see that the thermal neutrinos are strongly produced with the, say, energy luminosity ranging in between, say, a few times 10 to the 50 ergs per second each. And this can last for several milliseconds up to several seconds, depending on the lifetime of the central hypermassive neutron star. Okay, and those energies of the thermal neutrinos are roughly in the range of tens of MeVs. Okay, and one particular feature, if you are familiar with supernovae, then one particular feature of neutrino emission in merger remnant that is very different from supernovae is that you can see, for example, in left-hand side, during the first several milliseconds, then the electron neutrinos, the emission of electron neutrinos, which are shown as green lines, are actually a couple of times stronger than that of electron neutrinos, which are shown in the red lines. Okay, so this is due to the very simple fact that because the merger remnant initially, the two neutron stars initially having very low YE, say minor, smaller than, say, 0.1-ish. Okay, so once you heat it up, then you want to restore your composition to equilibrium. Then in the hot temperature case, then you would have a lot of positrons. Okay, so then in this case, the merger remnant must protonize, meaning that you have a positron captures on neutrons, and the consequence is that the merger remnant must initially emit more electron antineutrino than electron neutrinos. So that is like one signature of the initial neutrino emission from neutron star merger remnants. Okay. So, but given those large amount of energy being emitted per unit time and the average energies, then people also find that the neutrinos in the merger remnant environment can also largely impact the relevant conditions for nucleosynthesis. For example, on the left-hand side, yeah, this was taken from Radice et al. At 2017. They see that in the polar region, where closer to the symmetry axis of the merging plane, there are like electron fraction can be raised even higher than 0.3 by neutrino absorptions on nucleons. Okay, and similarly in 2017, where people also studied the ejecta YE distribution coming from the accretion disk outflow. Okay, and those outflows are mainly driven by the viscous processes. However, the strong neutrino, the presence of a strong neutrino flux can also largely affect the YE distribution inside the merger outflows, the disk outflows. For example, if you have like a 0-second lifetime, basically a prompt formation of black hole, then the electron fraction in the disk outflow would be around, say, 0.1 to 0.3-ish. Okay, but if you have a longer-lived hypermassive neutron star in the center, then you can see that as the remnant lifetime becomes longer, then the peak YE can be shifted to higher. Okay, and then you can also eject more material. Okay, so all those different studies shows that the neutrinos can play a very important role in determining, say, the properties inside the nuclear relevant for nucleosynthesis in merger ejectors that are the key to model the kilonovae. Okay, so one thing that has not been included in any hydrodynamical simulation is the flavor oscillations of neutrinos in this context. Okay, so then that brings to us the interesting topic of collective neutrino oscillations. Okay, so it was found back in almost like several decades ago. The first paper on this was like in 1987 by George Fuller et al. And then there were a lot of follow-up studies on this. Okay, and initially people focused on the context of quark-like supernovae, and what people found was that in the presence in an astrophysical environment where there are a lot of neutrinos being present in the environment, then when you are trying to describe the evolution of your neutrinos, okay, the statistical phase space distribution of your neutrinos in your environment characterized by a Wigner transformed flavor density matrix, okay, where the diagonal elements are basically the distribution functions, real numbers, and the off-diagonal elements tells you the flavor coherence or the degree of mixing for neutrinos that are having particular momentum p at the position x. And the evolution of those if you want to solve it, you basically need to solve a multi-dimensional quantum transport equation that is intrinsically a 7-dimensional problem. You have the derivative in time, space coordinates, and the phase space coordinates. And then you have the, on the right-hand side of your equation, you have the collision term, and then you also have the terms that has a complex number here, and there's a commutator of an effective Hamiltonian with the density matrix. Okay. And inside this Hamiltonian, there are like 3 terms. The first term is the typical term that describes the vacuum neutrino oscillations that we are all familiar with. And the second term is the one that's coming from the neutrino electron forward scattering that can explain the solar neutrino observations. Okay. And the third term is the one that can only be relevant in astrophysical environment with large neutrino flux or neutrino densities. And this h nu basically is nothing but the multiplication of the Fermi weak interaction scale GF times roughly the number density of neutrinos. Okay, but then here we replace it by density matrix. Okay, but this is looks not so different from say MSW term, the HM term, but because here it includes the neutrino density matrix itself. So this directly tells you that the presence of this term give rise the nonlinear nature to this problem, because if you want to solve this thing, then in the Hamiltonian you need to include the density matrix of neutrino itself. Okay, and we also know that in the present in the like supernovae or neutron star mergers, we have a lot of neutrinos going around. So the magnitude of this h nu term can actually dominate the magnitude of other terms. Okay. So in this sense, that this flavor oscillation system can be like in a strong coupling regime in the flavor space. Okay, so if you are in a strong coupling regime and you have a nonlinear coupling, then that tells you that your system can evolve collectively. Okay, from what we know in condensed matter physics as well, right? So this is basically tells you that this problem is difficult. It can multi-dimensional quantum transport, and it is a collective system. Okay. So yeah, so although it is very difficult to solve, but we have to make progress. Okay, so one thing that we did together with Irene back in 2017 was we try to examine the conditions of neutrino flavor configuration on top of the merger remnant disks. Okay, so what we found out was that the merger remnants, they can host a favorable, very favorable conditions for the so-called fast neutrino flavor conversions to occur. Okay, so this kind of, why do we call it a fast neutrino flavor conversions? That is because the outcome of this kind of flavor conversions can happen, or flavor conversions can happen in the length scale of roughly this inverse of the effective Hamiltonian of h nu, roughly the inverse of G Fermi times the neutrino number density. Okay, and if you put the relevant number of neutrino number density, that is roughly about, say, 10 to the 30 something per centimeter cube into here, then you can see that this is equivalent to the length scale of roughly centimeters. Okay, and then you know that your actual physical size or the length scale of your actual physical object is like a kilometer, several tens of kilometers. While now you see that this can bring up the problem to be even more difficult, because the relevant length for neutrino flavor oscillation is only centimeters. So you somehow need to do, if you want to fully understand this, you need to do the simulation that is a much smaller grid size compared to your merger simulations. Okay, and people also found out that over the past several years, I didn't include reference, but you can look at this paper to see all the relevant works, that to have the fast flavor conversion to happen, then it requires a condition so-called electron neutrino lepton number crossing in the angular distribution of neutrinos. Okay, so this is, what does this mean? This basically means that if you are sitting at a particular location inside on top of the merger remnant, where those two boxes are like the neutrino emitting surfaces. Okay, so if you are sitting at a particular location and then you look around you in your solid angle 4-pi space, then there will be some angular space where you have more electron neutrinos than electron antineutrinos, while in some 4-pi space you have more electron antineutrinos than electron neutrinos. Then that means that in this angular distribution of neutrinos, then there's a net lepton electron neutrino lepton number crossing. So this is the necessary condition for the fast flavor oscillation having the length scale of centimeters to occur. Okay, so what we did in this work in 2017 was that we used very simple parameterized two-disk toy models to look at this problem. For example, we assume that the neutrino number, electron neutrino and the electron antineutrino emission numbers, luminosities are like for example, 1.35, 1.35, and then the emission size of those emission disks are like 0.75. And then assuming that the relative height of the disk, this h, is roughly 25% of the width of the neutrino emission disks. Okay, and then what we found is that everywhere in this plot, this is like the growth rate or the growth rate of neutrino flavor mixing, or you can treat that like a conversion rate of neutrino flavors. Okay, above the merger remnant disk, the x-axis is the x divided by the size of the electron neutrino emitting disk, and the y-axis is the height on top of how far that is away from the emitting disk. Okay, then whenever, so this color code tells you the growth rate of this flavor mixing in the linear region. Okay, so you can see that everywhere on top of the merger disks, then there are like the neutrino flavor conversion rate can be as short as, say, few centimeter to the -1, given the typical number of the parameters input layer. Okay, so this was our first proof of that of our first examination of that the first flavor conversion condition actually can exist everywhere above the remnant. Okay, and then over the past couple of years, we did a few more works on this. And what we did was then we tried to analyze some more, instead of using the parameterized disk models, we tried to analyze the simulation data provided by people who conduct multidimensional hydrodynamical simulations, including neutrino transports. And we analyzed the results from, say, black hole accretion disk cases, and the case that contains very shortly after the post-merger, so in 2017 and last year. And what we found is that basically this conclusion holds also for those two different cases, that anywhere above the merger remnant, we find the condition for flavor oscillation, fast flavor oscillation to happen, and the growth rate of those flavor conversions are again usually in the length scale of centimeters. Okay. So then in those two follow-up works, we not only look at the instability conditions, we also further examine the possible impact of those flavor conversions on nucleosynthesis. Okay, so we made very strong assumptions that we assume basically this fast flavor conversion can lead to a full flavor equipartitions among all neutrino different flavors. Okay. And then we use this condition to recompute the new neutrino interaction rate, absorption rate with nucleons, that those two you see previously, to compute those two absorption rate of neutrinos and nucleons using this assumption. And we then recompute the YE distribution inside the merger remnant outflows. And then we then use our nuclear reaction network to see what comes out in the nucleosynthesis outcome. Okay, so those two plots shows you the results for the neutron wind in this black hole accretion disk systems. And then there you see that in the case of assuming no flavor oscillations, then the YE distributions are roughly ranging in between 0.3 and 0.5. Okay. However, when you include the flavor oscillation or flavor total equipartition, then the YE can be shifted from high values to say peaked around 0.25 in the neutrino-driven wind ejecta. Okay, and then for this particular kind of subset of ejecta in the system, then the consequences for the production of heavy elements are huge. For example, in the case of no oscillation, then you have very few lanthanides sitting there. While in the case when you have flavor equipartition, then this can be enhanced by several orders of magnitude. And also it enhances a lot of the second peak element production. Okay, and the reason is that these oscillations basically leads to smaller neutrino absorption rates. So because the increase of Y is mostly due to the neutrino absorption rates on nucleon. So when you have in the system, when you have smaller neutrino absorption rates, then you have smaller YE. Okay, so then you have more heavy elements basically. Okay. And curiously, when we try to do similar exercise for the early post-merger phases, the ejecta coming out, from the early post-merger phase, we find that it introduces the opposite effect. Okay, so for example, this is the ejecta around the polar direction, and then in this study, what we found is that when there was no flavor oscillations, then the neutrino in those ejecta, the YE of those ejecta are peaked around 0.4. And then when we now impose the flavor oscillation, fully flavor equipartitions in relevant for those ejecta, for neutrinos relevant for those ejectas, then we find that it actually increased the YE, okay, shifted the YE to the higher values, okay. And so then we also try to figure out what is the reason causing this difference. And then what we found was, in this case, instead of just, you still reduce your total or net neutrino absorption rate on nuclear, okay. But in this case, because initially there's already quite a number of, say, mu and tau flavor of neutrinos there, okay. So this full flavor equipartition processes actually, in this case, leads to a higher relative numbers of electron neutrinos relative to electron antineutrinos. And then because electron neutrino capture on neutrons produce, electron neutrino capture on neutrons, yes, produce the protons, right? So you actually, with the increased rate of the electron neutrino capture, you would produce higher YEs, okay? So the consequence of this is that you then get a much higher iron peak and the reduced second peak in the R process abundances. Okay, and in this case, we didn't find any changes. We didn't find much changes to the lensline mass fractions here. Okay, so so although in those two kind of simple studies, we find that the interesting conditions that can lead into the fast flavor oscillation can exist in merger remnant, and then they can lead to curious effect on the Y distribution in ejecta and on the associated nucleosynthesis outcome. But yeah, this is definitely not the end of story, because we, as I said in a couple of minutes ago, that we have made a very strong assumption that the flavor oscillation leads to full flavor equipartition. So this need to be, this is a very strong assumption, and the realistic outcome needs to be further established. Okay, and there were also like a very recent, and for example, the work done by Ian and Shashank and Irene, they try to address whether this kind of scenario can actually happen in the merger remnant. Okay, and then there was also a very recent work done by Lee and Siegel this year. What they look at is that whether this flavor conversion can happen even inside the merging disks, and what are the potential outcome. Okay, and what they found is that this can also produce similar to this case, that this kind of thing, if happened inside the merger remnant, can reduce the ejecta YE and give rise to stronger lens line mass fraction. So that was found by Lee and Siegel, and then we are also working together with Oliver Eust and some other collaborators to look at the similar setup. Yeah. So all these works basically points to the need that we need a very good and full understanding of the outcome of neutrino flavor conversions to emergers in order to say robustly predict the nucleosynthesis result and compare to kilonova data. Okay. So yeah,
so Meng-Ru, can I ask you a question here?
Sure.
So maybe it's from a few slides ago, and I've seen the condition of the lepton number crossing as necessary for fast flavor conversions before, but I've neglected asking before why this is a condition that is necessary, and so it is not evident to me. Maybe it's easy, but I'm missing it. Then my follow-up question to that is it a necessary or sufficient condition?
Okay. So yeah, very good questions. Yeah, so in fact, this was not clear for any of us until this year, actually. Yeah. So so like in the past, what we found was by numerical studies that to have fast flavor oscillations, that you need to have this. Okay, without this you cannot. Okay, but then this year there was a very interesting article coming from Morigana. Yeah, if I remember the name correctly, from a Japanese fellow. Yeah, he actually showed rigorously that this is a necessary condition, not only a necessary condition, but also a sufficient condition. Okay. And well, there was some, there could be some potential loophole in the case of sufficient condition. But I think there's no doubt that it has to be a necessary condition. And there wasn't, I don't have a particular simple, say, analog to say why this is a necessary condition, but I can send you the link afterwards if you want to see the proof.
Yeah, of course. Thank you.
Yeah. Okay. Yeah. So this is a part about the nutritional flavor oscillations. Yeah. So well, if there's and there any like other question related to this part? Okay, then if not at present, then I will go ahead to the next part. Okay. Then the next question I would like to discuss today is can we find other evidence of the presence of heavy elements in mergers? Okay. So we already see before in the beginning slide that the spectrum of the kilonova photons are sort of like a featureless. Okay, there was a particular example of strontium that has a very broad absorption and emission lines potentially. Yeah, but for other elements, it's very difficult. And this is basically reflected by the fact that there are many nuclei or many isotopes in the ejecta. So there are many lines, and then the merger ejecta expands with the semi-relativistic speed of 0.1 to 0.3 C. So there are very strong Doppler broadenings effect. Okay, so coupling those together, then you basically mix up all the lines. Okay, so directly seeing those absorption or emission lines of some elements in kilonova is difficult. But then the question we asked was, is it possible to associate the light curve to some particular presence of specific nuclei. Okay, so these ideas come from the fact that we know if we just look at, for example, the bolometric luminosities coming from any transient events powered by some energy injection. Okay, then the post-peak light evolution of this bolometric luminosity as a function of time is basically proportional to the energy input coming from the powering source. Okay, so then you can immediately see that, okay, now if in my R process element, if in my merger ejectors, if the heating, nuclear heating that powers the kilonova is contributed from many different nuclei that are, each of which is beta decaying, and then any of them are having somewhat different decay lifetimes. Okay, and then because of Q beta, basically roughly the beta decay energy release is roughly similar for given lifetimes, then you can basically like as equivalent to superimpose a lot of exponential curves at many different time scale altogether that will gives you a power law behavior of the energy production rate as a function of time. Okay, so this was confirmed by numerical simulations of the R process. Okay, however, if the heating can be dominated by a single or just a couple nuclei, then this power law can be broken down. Okay, so you may possibly see the exponential shape in your heating rate that powers the kilonova-like curve. Okay, then if we look at, for example, the number of R process nuclei that are present, if we look at how many R process nuclei that are there within, say, per logarithmic things in their half-lives, okay, ranging from 0.1 days to 100 days, then you see that the R process nuclei initially before, say, 10 days, per logarithmic intervals, they are almost like more than 20s. And then most of them are beta decaying. So that will give you this power law shape of the heating rate. However, at late times, after 10 days, there are only a couple of nuclei that can decay within this time range. Okay, so these are parts. So this already tells us that it may be possible in the very late time, if we say after 10 days-ish, after the mergers, to associate to identify the bolometric luminosity features with some particular nuclei. Okay, so this is actually. Yeah.
Can I ask you something with respect to this figure on the right? They include the kind of nucleus that is decaying, because I think the lifetime is not the same for all of them. So is this automatically included in this histogram, or is just one nucleus?
Yeah, so this is included. So this is like, for example, between say 1 day and 3 days, there are like 26, 27-ish nuclei that can decay, that are having this lifetime between 1 and 3 days. So this is what this is telling. Sorry.
Yeah, thanks.
Okay. Yeah. Okay. So yeah, so this number of potential decay nuclei at a particular time can reduce or can be small at a late time. Yeah, can already be seen that tell us that later it's possible to identify some features at late time. Okay, so this is precisely what we did in this work in 2019, where this is sorry that for the busy plot, but here you see that in the x-axis is the time, and the y-axis is basically the total energy heating rate to the ejecta, or equivalently the late time luminosities. Okay, and then there are 5 lines here, and each of which corresponds to a different models describing the composition inside our ejector. Okay, so the red lines, there are 2 of them. They are corresponding to the low YE components, where you produce a broad range of R process elements, ranging between mass number 50 to 250-ish, at time of the day. Okay, and then for the green curves, they correspond to the high YE cases, where you only produce mass number elements of mass number smaller than 130-ish. You don't produce much of the heavy elements above the second peak. Well, there's another blue curve that corresponds to the same composition, the same Y distribution as model A, but using different nuclear physics model that gives you more actinides, particularly in the mass range of 220 something here. Okay. So clearly you can see that if you normalized the energy production rate around times of a day, yeah, so that they can sort of comparable to the GW17 or 17 data. And then you can see that if you do this normalization to fit the peak lights, okay, then the light curve prediction at late time can diverge. Okay, so this is interesting. Yeah, so for the low IE cases where you produce a broad range of the abundances, then this late time light curve basically still reflects the power law behavior that we were talking about of Q dot. Okay, and then for the high YE case where you have much fewer nuclei present, then you see there could be a dip around 20-ish days, and then there could be another bump around 100 days. Okay, while in the case where a particular model that gives you some higher yields of actinides, then you can see an extended bump ranging in between 10 and 100 days. Okay, so yeah, so those are very curious features that can potentially be observed in future observation of neutron star merger events. Yeah. So for this GW17 or I-17, unfortunately, we didn't see much after roughly 20 days. There were like some data there, but they were the lights are only collected in particular band. So you cannot use this to infer the bolometric luminosity. They can only be used as, say, lower limits. Okay, so we cannot apply this to this observation, but we're hoping that, say, for example, in the future, yeah, if we can really see the light curve shape all the way out to, say, 100 days, then this might help us to distinguish different composition models. And yeah, I think I will skip this one. So particularly interesting is the comparison for us is kind of comparison between this blue and the red, where you see very extended bumps. Okay, the origin of this bump is actually coming from just 4 alpha decaying nuclei. Okay, so if you look at the nuclear chart, then you see that there's a region where you have a mass number of 220 something, basically radon and radium. And they have like a decay lifetime of, say, roughly 4 days and 10 days-ish. Okay, and then each of them, if they decay, they can go to a nucleus that is having much shorter lifetime. So this is like once they decay, they will immediately go back to the instability in the timescale of days. Okay, so effectively each of them, if they decay, they will produce or they will release 30 MeVs per decay chain. Okay. So this is much bigger compared to, say, beta decay energy release that is roughly 1 MeV-ish. Okay, so that is actually why. Yeah, sorry.
Sorry, I think Marcus had a question.
Sure.
Yes, thank you. Exactly on this figure here, I was wondering, in the one that you had just now with the luminosity, the light curve. Yeah, this one. So I wonder if I read this correctly. So you have like this black data points that sort of match the different models here, but you said that the triangles are upper limits on the luminosity.
Yeah, so those triangles, hollow triangles, after 10 days are lower limits.
They're lower limit. So,
yeah, because those are like only contains only data from some photometric bands. So it is not covered. So the bolometric luminosity, you need to integrate it over the wavelengths or the spectrum, but these are only part of it.
So okay, it's interesting that this is a lower limit and not an upper limit. But so you say that all the curves here are consistent with these lower limits, yeah?
Correct. Yeah.
Okay.
Yeah, you can also see there are actually 2 inferred lower limits here. I don't know if they actually resolved this. So this was analysis by 2 different group of people from Spitzer data.
I see. Okay, thank you.
Yeah. Okay, so yeah, so the key point here is that although in comparing the blue and the red, the difference of the actinide abundances are like only a factor of 10-ish. But they can make a big difference in terms of, say, the energy production at late time. Okay, so yeah, so this part is just to show that indeed, if you have those 4 different nuclei that are having, say, number fractions as low as a few times 10 to the minus 5, then the energy production rate shown by those blue curves can dominate that from the beta decay, all different beta decay nuclei. Okay, all those below, say, the late peak. Yeah, so beta decays are produced by those group of nuclei, and alphas are from those. Okay, yeah. So yeah, this was suggested by us that well, if we can really collect all the lights among all different bands at late times, then this bump feature may be used to, as say, as a kind of an evidence to say there are existence of alpha decaying elements or nuclei. Yeah, or say they can, if we don't see this, then we may be able to put a constraint on the production of those alpha decaying actinides. Okay. Yeah, a similar story can also be said, for example, for particular nucleus that can fission at the timescale of roughly 60-ish days. Yeah, this is a nucleus called Californium 254. And yeah, similarly, if this guy is present in the ejecta, and then if it can decay, but if it has to decay, right? It has to do spontaneous fission. So if there are some amount of it there, say roughly abundance is roughly larger than 10 to the minus 6, then they can also predict that it can produce a different bump that is around, say, after 20 to 30 days in the bolometric luminosity. So if one sees this, then yeah, this can be potentially used as a evidence to say, actually, in this part, in one of the particular merger event, the Californium 254 can be produced, and this can have some potentially, hopefully, implications for the ejecta properties or even for the uncertain nuclear physics beyond experimental reaches. Okay. So yeah, so I think I sort of run out of time, so I would just skip the last part, and sorry about that, and just jump to conclusions. Yeah. So okay, so what I covered today was, say, initially we spent some time for introduction, say the identification of lanthanide actinide mass fraction in kilonovae associated with GW17 or 17 provided the first evidence that mergers are possibly the dominating producer of R-process elements. And then we discussed a bit about the potential roles of neutrinos, and then we say that, okay, the flavor oscillations, particularly the faster flavor oscillation, are likely to happen in those merger remnants, but we still need a much better numerical modeling to see what are the real impact. And then we, just minutes ago, we discussed that the late time light curve of kilonovae can potentially offer opportunities to infer the presence of small amount of translated nuclei and or even fissioning nuclei. Okay, so yeah, that's it, and thanks.
Thank you very much, Meng-Ru. It was super interesting and educational for me. Do we have any questions for the audience? From the audience, sorry. I think Irene has one.
Yes, I wanted to ask about the last part. So there are all these lower limits, and you were mentioning that in order to match the theoretical predictions, we needed to measure at other wavelengths. And I was wondering, what are the prospects for the future? And then also, what are the chances to actually identify the right nuclei? Because as we know, there are many degeneracies in this game. So yeah, I was wondering whether there are prospects of improvement for the future.
Okay, so yeah, good questions. Okay, so yeah, what we also show in this slide, in this plot, is that for example, we put the JWST if it's going to be launched, limits in the mid and the near infrared bands. Okay, assuming that there's a merger at 100 megaparsecs. Okay. So you can see that if we can have JWST time to look at some of the merger event at this length scale for some extended period to collect some data points there, then in principle, because out of this daytime, we think most of the lights are emitted in the infrared band. Okay, so although we probably cannot predict the precise spectrum information, but if we can collect all of them, then we should be able to recover what is the bolometric luminosity. Okay, so if we are able to do that, then it is possible, I think it is possible to compare what we say here to future data. Okay. Yeah. And
Okay,
the uncertainties, of course, there are of course some uncertainties, right? So for example, in those late times, one key issue is whether there can be like mechanisms that delayed the energy being dumped from nuclear decay to when the photon comes out. Okay. In particular, at a very late time, the conditions can be similar to the nebula phase in, for example, supernova, where the recombination of electrons can be pretty much uncertain, especially for the R-process elements. So definitely we still need further study to really confirm whether with this exponential light heating shape, we can, and with the very good nebula emission feature modelings or the emission time modelings, we can still have this unique bump feature. But yeah, this would need to be done in the future theoretical studies.
Thank you.
All right. Maybe one related question that I had is, do you expect to get more late time data from GW 170817?
Probably not, right? Yeah, because we are already almost 4 years, so we are out here. Okay, yeah. So for the light coming from the kilonova is pretty much very dim at this moment. Yeah, people were still getting like last year or 2 years ago, they were still getting the radio emissions that is potentially coming from the jet or ejector interacting with ISM. Yeah, the radio band, but not relevant for this in the infrared band.
Yeah. Okay. All right. Do we have any final question from the audience? I don't see any.
I have one more.
Eden has one. Yeah.
Like I was wondering, also in order to do this computation, you also needed to worry about the host galaxy, right? So if you don't know how dense it is, then you can also confuse some of these lines.
You mean for the kilonova spectrum?
Yeah.
Not really, right? Because yeah, those are basically produced within ejector itself, right? So if we are talking about say radio emissions that are coming from potentially interaction of jet versus ISM, then we need to know the host property, the host galaxy property, as you said, right? But for those kilonova emissions, they are mostly dominated by the kilonova property itself, or the ejector property itself.
Yes, I meant for observations. So what I observe also is affected by the galaxy. I agree that for the theoretical computation, we don't need it, but for interpreting the data that we see can be affected from.
Also, you are wondering like if there are any contamination.
Yeah, exactly. Right? Yeah.
Okay.
Yes.
Okay. Yeah. That I'm not sure, but I don't think so, right? Because you need to have a very strong emission in infrared after this luminosity. Yeah, probably not easy, but I'm not sure. Yeah, you need to check.
Okay, thanks.
All right. I don't see any more raised hands, so thank you again, Meng-Ru.
Yeah, thanks.
We hope to be able to have you in person and then not very distant future now.
Thank you. Hopefully so.
Yes, and to everyone else, thank you. This will be our last Astroparticle seminar before the summer break, and we'll return once activities resume after the summer break. So thank you for being with us all throughout 2021 so far, and we'll see each other soon. Thank you again, Meng-Ru.
Thanks.
Thank you. Bye.
Thank you.
Bye.